So kinetic energy is energy possessed by a body by virtue of its motion. And we write, let's say, K E equals to, we express it as 1 by 2 m v square, and v square can be written as v dot v. This dot product gives v square. So 1 by 2 m v square. Now, we have several examples of kinetic energy. And let's say, one example, we use kinetic energy of running water to produce electricity. Yes, running water falls on turbine and it rotates, and then that turbine is connected to dynamo and we get electricity. So in hydroelectric power plants, so moving body possesses energy to do work. Okay, now we are going to continue work done by variable force. Look, till now we have discussed about work done and we were taking force to be constant only. Now we are going to express how can we obtain work done if the force is variable. Let's say the force is varying with displacement. So let me write here, work done by variable force. Okay. Let's say a body is moving. For simplicity, we are starting with one dimensional discussion. So a body is starting from here. Let's say this is xi, initial position, and it reaches up to here, xl, final position. And during this, it experiences a force which is changing with position x. So force is a function of x here. Now, if we want, what will be the work done if a body moves from here to here under the influence of this variable force? So for that, we have to do one thing here. We can look, the force is varying over the entire displacement, but we can take a very small displacement here, let's say delta x, and for this delta x, we can consider force fx is constant. Over a small delta x, we can consider that force is not varying much about, yes, we can consider the force is constant. And then we will have small work done for this displacement delta w, and that delta w we can write as force. Now we are considering it is constant into this delta x. And if we fragment this all displacement in delta x, delta x, smaller elements. So we can get total work done by adding just this delta W. So we can write addition of this delta W. So we can write fx dx delta x, and x is varying from xi to xf. We can express in other way also, but let's say this way. So we can do small fragmentations of this displacement, and over those fragments, a small yeah, elemental lengths, we can consider force to be constant, and then we can multiply force with these elemental lengths delta x, and then we can get small work done, elemental work done here, and then we can add all those small w delta w, and then we can get the work done from here. Yeah, work done uh, on the body from here to here. Okay, so this is one way. We have just fragmented this displacement, and then we can do this way. Now, if we are choosing one more thing here, and we are taking limit that delta x is tending to 0, that is very, very small. Okay, then we have work done equals to almost limit delta x tends to 0, and then summation over from initial x to final x fx delta x, and this thing we represent as integration, a kind of continuous summation, we say integration. So it is running from xi to xf, and then we have here fx, and with this notation we used to write dx, this elemental length. So we have work done equals to integration of fx dx. Fx means force, which is function of x, and dx elemental length. So fx dx integrating from initial x to final x. So this is for we can say this is a kind of continuous summation. This is discrete one. If you are not taking limit here, this is discrete one. We were choosing delta x, delta x, delta x, those discrete values. And if we are choosing delta x and we are tending this delta x to 0, this will give us a kind of continuous summation which we represent as integration sign. Now, work done is xi to xf fx dx. Okay, let me explain what is it geometrically. So let's say we have obtained a plot of fx versus x, and then this point here is initial x, and this point here is final x, and here corresponding to this initial x f xi, and here corresponding to this final x we have f xf. Ultimately this is graph for function fx. Okay, so now what does it mean? What we have done here, look, I want to go back to this summation. Yeah, here, look. What we have done, we have taken small length here, and then corresponding to that small length, let's say delta x, we can consider f to be constant over this region. So what we have done, we have taken x to be constant, fx to be constant here. Then we have a rectangular shape here, and this rectangular shape we can obtain its area as fx into delta x. So we have delta w. What is delta w? Geometrically, it is area under this curve, and this curve is nothing but a plot for fx versus x. So this area represents delta w, and we can slice entire region under the projection of this graph. On the x, we can slice all regions. Look, here we can take also delta x, and so on. We can take from here to here so many things. So we can say w is summation of all those smaller areas. So fx delta x, and just repeating that. And if we are taking delta x to be 0, within this limit, we will get w equals to this much. So work done finally is here, geometrically it is area under this curve. This area, I'm trying to set that region here. So this area entire to here all the way. Okay, so this area is, yeah, I'm just doing it roughly. So this area is representing work done, and with integral form we can write xi xf fx dx. So geometrical meaning of work done for this plot is the area under this curve. What is happening here? In a test, bullet is fired, and this bullet has mass of 50 gram. Let's say this is bullet and it has mass of 50 gram. So we can write 50 into 50 into 10 to the power minus 3 kg, and it has initial velocity, you can say 200 meter per second. Okay, it passes through an obstacle of thickness 2.00 centimeter, and then what happens after it passes through the obstacle? Its kinetic energy reduced to only 10% of its initial kinetic energy. So if kinetic energy here is K, here it has kinetic energy only 10% of K, or you can say K by 10 only. Now what we need to calculate? We have to calculate here emergent speed, that is the speed here. Let's say this speed is something, let's say this is V naught, this speed is V. So we know kinetic energy is 1 by 2 m v square, and that is equal to k by n, here kinetic energy. So we can write here 1 by 2 into mass of the bullet m v square equals to 1 by 2, here kinetic energy, this one k is 1 by 2 into mass of the bullet into v naught square and whole divided by 10. So this thing is not going to survive, and this thing also. Now we have v square equals to v naught square by 12, and v naught square is 200. So you can write here 200 into 200 by 10, or you can write, let me demarcate here. Okay, you can write v equals to 200 by under root 10 meter per second. You can calculate it into decimal, and then if you go in well detail, you have to keep in mind the significant figures involved here, and then you have to go for least significant figure. And what is the least significant figure here? It is uh, here 50.0 gram. It has three significant figures, so you can go up to a single significant figure here. So that thing we have discussed already, how to return the number of significant figures in accordance. So I am not going to do the same thing here again. It will be a lengthy process again, but if you want, you can go for that. Now moving to next example. In this question, what is happening? A woman pushes a trunk on a railway platform which has rough surface, and she applies a force of 100 Newton over a distance of 10 meters. Thereafter, she gets progressively tired and her applied force reduces linearly with distance to 50 Newton. So, the total distance through which the trunk has been moved is 20 meters. Now we have to plot the graph. What graph we have to plot? Force versus displacement graph we can plot. So let's say on this axis, which we consider dependent axis, we are plotting force applied by the woman, and on this axis we can plot displacement. So up to first 10 meter, let's say up to here, the woman applied a constant force of 100 Newton. Let's say up to here, women applied 100 Newton force. Okay. After that, for next 10 meter, she applied uh, linearly reducing force to 50 Newton. So from 100 to 50 for next 10 meter, that is up to 20 meter. So this yeah, I'm just indicating with red. This red graph is showing the force. First half it is constant 10 100 meter up to 10, 100 Newton up to 10 meter, and in the second half it is reducing linearly. Look, this is a straight line graph. Now what we have to plot, we have to plot the force applied by human and of course the frictional force. Okay, we can calculate frictional force also here, but we do not have to calculate because it is given, which is 50 Newton. So look, friction force, if we are plotting this way, friction force should come to this side because it is opposite to the direction of displacement. So if we are taking this force along the direction of displacement, then friction force we have to represent here with minus 50 Newton, and this force is a kind of kinetic friction, and this will be constant up to this 20 meters, means during its entire journey. Now what we need to do, we have to calculate the work done by the two forces. So first one, the applied force, and second one, the frictional force. What we need to do, we have to calculate the area under this curve. Look, if you are going for this curve, you can separate it into two different segments. One up to 10 meter, another up to from 10 to 20 meter. So this area, let's say this is W1 and this is W2. This area is how much? This area is 100 multiplied with 10. Okay, so work done by the applied force by the woman is 100 into 10. I'm directly writing here Newton plus C is continuing up to 20 meters. So now we have to calculate this area, and if you look carefully, this area is how much? 1 by 2 into sum of, look, this is a trapezium, so you can write half and sum of parallel sides, that is this length plus this length, these two are parallel sides, so you can write 100 plus 50 multiplied with height, and height here is this one. Look, this is height here, the separation between these two parallel sides, so this is 10 Newton. So you can calculate it how much it will be, and then how much it should actually 100 into 10, that is 1000 here, and let's say 1000 Newton plus, and this one is 5, and this one is 150, and then it will be 150 times 5, that will be 750 Newton. So ultimately it is going to be 1750 Newton. This is work done by the applied force. Okay, the woman is applying the force. Now we have to calculate work done by the friction force. And in that case, we have to calculate, let me use another color. You have to calculate area under projection of this curve, means this area we have to calculate. And this we are going to get minus 50 times 20 Newton. This work done is negative actually. It is reducing its energy, kinetic energy you can say. So this will be minus 1000. Work done is in Joule. Of course. Okay. So work done is in Joule. So work done by the woman is 1750 Joule, and work done by uh, friction force is 1000 Joule, which is negative. Okay, coming back to our discussion, work energy theorem for variable force. So how can we continue? Let's say we have kinetic energy changing with time. So we can write dk by dt. What we are studying now? Work energy theorem. Work energy theorem for variable force. Okay, we have already uh, derived the expression for work done here in case of variable force. Now we are going back to work energy theorem. So we can write it d by dt. This is rate of change of k with respect to time. Okay, so 1 by 2 m v square. And for a moment, let's take mass to be constant. We are not, yeah, we can of course study for variable mass, but for a moment, to keep it simple, let's take mass to be constant. So we have here dk, rate of change of kinetic energy with respect to time, will be 1 by 2. I am taking out. Then we will have dv square by dt. But we know that we can apply chain rule here. We have dv square now. So we can apply here chain rule this way. Look, now we can differentiate this v square with respect to v. So it will be, let's say, dk by dt will be 1 by 2 into m, and this will be 2v, and then we have, okay, mind it, this is not dot product now. I'm just writing. So this will be dv by dt, that is rate of change of velocity with respect to time. And if you know this term, you can write here mv, this 2 and this 2 are going to cancel out. Mv and dv by dt is acceleration. So mass times acceleration is force, and then we have velocity. So dk by dt, we have f into v. Okay, I'm continuing from here. So let's move to the next slide. dk by dt equals to f into v, and you know v you can write as rate of change of position with respect to time. Look, we are dealing this thing in one dimension. We should mention this. We can generalize it, but to keep the things simple, we should start with simple considerations. Okay, so it will be dx by dt, and now you can check here dk will be f dx, and now you can see that this is change in kinetic energy, this is force, and this is displacement. So change in kinetic energy is work done. If you are going from some initial kinetic energy to final kinetic energy, let's take integration both side. Okay, so we can take dk here. Let's say it is going from initial kinetic energy to final kinetic energy, and here from somewhere initial position to final position fx dx. Okay, so it will be final kinetic energy minus initial kinetic energy equals to, and look, don't write here f x final minus x initial. This is not going to work here. Why I am saying that? Because force is variable, and if it is varying with x, then this term is going to give us some different value after integration. So this force, till now we don't know what is the exact form here, but we know that this is varying with x. So we are not going to take it out and write xf minus xi. So we should avoid this common mistake. So we can write here directly. This is, we have already introduced. This is nothing but work done by this variable force. This is work done by this variable force when the body is moving from initial position xi to final position xf. So we have come to this work energy theorem in case of variable force also, and it is saying the same thing, that change in kinetic energy is equal to work done. Okay. Now I would like to comment on these things. Newton's as work energy theorem is a kind of integral form of Newton's second law of motion. We have obtained this thing from there. So let's take here just a moment. Okay, so let's take here second law of motion and here work energy theorem. Okay, now Newton's second law of motion, if you write it in a complete manner, it will be this way. So F equals to m into a. But look here, we can add these vectors here because a acceleration is a vector quantity, force is also a vector quantity, and this mass we can take it constant for timing. In work energy theorem, there is change in kinetic energy equals to work done, that is F dot S. So the first thing we can say, look, the Newton's second law of motion has information about directions, but this thing is going to give us a scalar quantity. So in work energy theorem, we do not have information about the directions. So I can write this thing contains information about the directions, but this does not. Now, second thing you can see here, Newton's second law of motion deals at instant of time. So we can see here instantaneous thing is this. This we are dealing at particular instant of time. That is, if we are writing a t here, so we are saying that at particular point of time, what is the acceleration, and corresponding to that acceleration, what is the force is experiencing that body about which we are dealing. So this is for instantaneous time, but this thing is dealing in a time interval. Why I am saying this? Here time interval is involved because we say that from here to here, from initial position to this final position, this body has moved and there is change in kinetic energy. Look, there is displacement. Let's say this is displacement and force is acting over this displacement on the body, and then we have work done here. So we are saying that from here to here, and to move from here to here, there must be time interval involved. So if not explicitly, but implicitly, time interval is involved here because we are dealing in an interval. So, but here what is the case? Here we are dealing at particular instant of time. So these two things I would like to indicate. And why? Because when we go to solve numerical problems, we have to apply these things based on the requirement. What are the things we have to deal with? So somewhere this second law of motion will be useful. Somewhere this work energy theorem will be handy. Okay. Let's end our discussion with one last example. So, okay, here we have the last example. A block of mass 1 kg moving on a horizontal surface with speed, initial speed 2 meter per second. So, we are dealing in one dimension only. So, let's say this is horizontal surface, and on this surface, let's say a block is moving. Okay, so mass is 1 kg. It makes simple our calculation, and initial speed is 2 meter per second. That's good. 2 meter per second. Enters a rough patch ranging from x equals to 0.1 meter, 10 meter to x equals to 2.01 meter. Let's say this rough patch starts here 0.10 meter and it ends here, let's say 2.01 meter. Okay. So This is rough patch. So what will happen if this block comes here, and from here it will start experiencing a retarding force, and we know that force friction. So this friction will be acting on this block from here to here, this range. Now this is given as minus k by x for this range, and this friction is 0 elsewhere. So this block is not experiencing any friction in this region, and of course in this region. I am just indicating the rough region with this red mark. Okay, so this is the region where the block is going to experience this friction. Now K is given. K is given as 0.5 joule. This K. What is the final kinetic energy and the speed of the block as it crosses the patch? So the final kinetic energy we will get here after this block crosses this patch. And now the final kinetic energy will be reduced one. So initial kinetic energy is here. Half mv square we can take. Let me write here. Initial kinetic energy is 1 by 2 mass, which is 1, into initial velocity squared. So this is 2 square. That will be 2 joule. Now final kinetic energy will be, look, whatever be the initial kinetic energy and work done by the friction, which will be negative of course. So we have to reduce that work done by this frictional force, and then we will get final kinetic energy. Okay, so look, this frictional force is not constant. This is varying with x. So we have to apply the concept of work done by variable force, and then the work done will be from 0.10, that is initial x, xi here, and xf is here, which is 2.01, and then f, which is minus k by x dx. This way we can get work done by this frictional force, and then it will be minus 0.5. I'm writing k equals to 0.5, and as it is constant, I'm taking it out. So, and look here, we will have 0.10, 2.01, and then we have dx by x. And integration of 1 by x with respect to dx will be log of x. So this will be minus 0.5 ln natural log. Natural log, you know, natural log is log with base e, and there is another log with base 10. So this log we call natural log, and we represent as it is represented as ln, and this we simply represent, although it is not very strict for this, but yeah, for simplicity we can represent it as log, and this is represented as ln, natural log, or log base e. So what we are going to get here, ln, and then this 1 by x dx has integration of ln x. So ln x, and then we have lower limit 0 point. If you know integration, then well and good, and if you don't know, you can check that, yeah, there is a formula that will be integration of 1 by x dx will be ln x, and of course there is some constant here, but if we take lower limit and upper limit, this constant gets eliminated.